Hey students, welcome back, welcome again. So we are back in action with ligands. In the last video we have discussed about the basics. If you are looking for the Hindi version, visit our channel's playlist. Now, what is ligand? I have told you in the last clip that if you have a coordination pair like this, the first species is our central metal, which is an acceptor, and the rest is ligand, which is a donor. So it donates electron to the central metal in order to get bonded with this. This is our ligand. It is just a donor of electrons. Now, if you want to study ligands, we have three different categories. First is on the basis of charge. We will classify them on the charge it carries. Next is on the basis of denticity. We will classify the ligand on the basis of number of lone pair donated and on the basis of type of donation of lone pair. This is a different one. So we will approach this 1, 2 and 3. Here we go. On the basis of charge, we can say we have three types of ligand: a positive ligand, a negative ligand, or a neutral one. Very simple. Positive ligand, the list is very short and you might not see much. NO plus, NO2 plus and NH2, NH3 plus. Nitrosonium, nitrosilium, hydrazinium. So, these are the three positive ligands. These have positive charge on them. Now if you look here, NO, it is an important case. We have discussed this in the video of IUPAC nomenclature. The link is in the description box. Now, negative ligands. Negative ligands have a very long list. Halogens, Cl, Br, I, F, also sulfate, carbonate and cyanides and many other. SCN also, NO2 also. So any ligand carrying a negative charge is a negative ligand. However, there are few cases we need to discuss. There is one particular ligand that is also negative, that is DMG. Another one is ACAC. So these are two very important ligands as far as our syllabus is concerned. These are also negative. And one more I think I have in mind for negative ligand, oxalate ion, C2O4, 2-. So these are the negative ligands, charge carrying negative. Now the neutral ones. The neutral ones, the list is again very short. NO, CO, the next is NH3, H2O and benzene. I will write it benzene, pyridine. Pyridine looks like this, very beautiful. This is pyridine. So these are the neutral ligands. These do not carry charge. Now look here. NO is positively charged. NO is neutral also. So how will we judge which one is positively charged, which one is neutral? So NO plus, it is common one. It is very common and found in most of the examples. NO neutral, it is highly rare. Not rare, rarest. It is an endangered ligand. Very few examples in our syllabus where you find NO to be neutral. And we have discussed the cases in the IUPAC video. The link again in the description box. So this is the basic classification on the basis of charge. Remember this, NO is positively charged as well as neutral. Rest is, you know the story. Now let me move on to the denticity section. First, I will need to clean this up. If you want, you can take a good screenshot and write this down. So, what is denticity? Denticity is basically the number of lone pair donated by ligand, by the ligand. So the number of lone pair donated by our ligand will be our denticity. Suppose the ligand donates only one lone pair, then denticity will be mono or the ligand will be monodentate. So the first case is monodentate ligand. So the monodentate ligand, the word mono means one, single. One lone pair will be donated towards the metal. Now the examples: water. Next up is ammonia. You can have CN, all the halogens, F minus, Cl minus, Br minus, I minus. And for more, I think any particular example will do fine. Let it be. So monodentate, one donation, one pair of lone pair is donated. Next up we have is bidentate. It is important because the cases are very much missing from our books and they are far apart from each other. So I will try to compile them at one place. First of all, bi means 2. There will be donation of 2 lone pairs. Now the examples: EN, ethylene diamine. Look here, CH2NH2 and CH2NH2. Now I will change the color so that I can show you the donor atom. This nitrogen has a lone pair. If you know the basic bonding, this nitrogen has the lone pair. The basic bonding, it is one donor. It is donor number 2. We have 2 donor atoms with one lone pair here, one lone pair here. Ethylene diamine, that is EN in short. Ethylene diamine or ethane 1,2-diamine. It is a bidentate ligand. Next we have is DMG with a minus. It is also a bidentate ligand. However, if you look at the structure, look here, CCCH3, CH3, NOH and N, there will be a double bond, O minus. It looks like that, and the donor atoms are here. So we have again 2 donor atoms. So these are the 2 common cases of bidentate ligands. Next up we have is oxalate ion, C2O4 2 minus. It is also a bidentate ligand. Look here, CO, CO, O minus, O minus. These are 2 our donor atoms. So bidentate. So these are the cases of monodentate and bidentate. In bidentate, I would like to discuss this DMG for a particular cause because it has been asked in most of the exams. So I will clean this up first of all. Now we have a question that what is the use of DMG? First of all, I just need to explain the full form of this. DMG, dimethyl glyoxime, and it is DMG. I must say dynamite. It is very important, so important that I am going to write down my autograph next to it. So what are the questions asked from DMG? First of all, what is the use of DMG? DMG is used for the estimation of nickel 2+ ion. Question, answer. What is the use of nickel? What is the use of DMG? Nickel estimation. Next up, when it combines with nickel, which complex is formed? What is the color of the complex? What is the structure of the complex? At what pH this complex is formed? Is there any additional bonding? How many membered rings are formed with DMG? So these are all the questions. These questions are asked in IIT, AIIMS, as well as NEET. So the only question, the only ligand that has made this big is DMG in all the 3 exams. Now what happens? Look here. If you have an Ni2+ species and you treat this with dimethyl glyoxime, DMG, in the presence of a base, in the basic medium, NH4OH, it will form a complex with 2 units of it, NiDMG whole twice, and this complex is cherry red or brick red. So this is the first question. The reaction is carried out in a basic medium, so the pH will be basic and the exact pH will be around 9 to 11. This is the first question asked in our exam. What is the pH at which this reaction occurs? It has been asked in AIIMS. So the pH is 9 to 11, or we can say it occurs in basic medium. The pH is what? 9 to 11. So the first question done. Next up, it has been asked what is the color of the complex, that is cherry red or dark red, or you can say brick red. Finally, the question asks that what is the structure and what is the number of membered ring forms in this particular case. Now for the structure, look very closely because I will sketch this very beautifully. Grab a paper and a pencil so that you never miss this. First of all, I will sketch a DMG. Look here very closely. So this is our DMG molecule. Let us consider this our nickel Ni2+. Okay, this is our donor atom, donor number 1, donor number 2. So the donation occurs like this. Here we go and here we go. So we have two DMG species. One of them will be this side. So I am going to sketch this one also. Just give me a second so that I just do it. NO. I will flip the molecule this time. Just for better understanding, I will flip the molecule so that you get the point. So this is our second DMG. Same goes with this and same bonding is done. This is our lone pair and it is donated to our nickel molecule, nickel atom actually. So the question asked is what is the member, how many rings are formed in this case and what are the members of the ring. So look here, first with nickel on the left side 1, 2, 3, 4, 5, a 5-membered ring with DMG molecule on the left. Again 1, 2, 3, 4, 5, again a 5-membered ring with DMG molecule on the right side. But there is one more ring, two more rings. If you look very closely, you have this OH and you have this OH. This OH is negatively charged, partially negatively charged due to the electronegativity of oxygen and electropositivity of hydrogen. This is proper negative charge. Same goes here, a minus here, a plus here. And now plus minus sure short attraction, there will be bonding. Plus minus sure short attraction, there will be bonding, and this is what? A hydrogen bond, a weak bond which binds both DMG molecules. Now look here, the number of members in the ring. Nickel 1, 2, 3, 4, 5, 6. A 6-membered ring here, a 6-membered ring here. Look, 1, 2, 3, 4, 5, 6. A 6-membered ring here and a 6-membered ring here. Now this is an interesting one. The additional hydrogen bonding will provide us 2 more rings of 6-member. So the hydrogen bonding will give us 2 different rings of the same type with 6-member. However, with DMG we have 2 5-membered rings. This is the most important question asked in our JEE. So this is all about DMG: color, pH, structure, bonding, donor, acceptor and the complex. So sketch this beautifully before it flushes your mind. I will just rub not all of it but just a bit so that you have a good screenshot of it. So we will just skip to the next part. One thing I want to tell you, DMG forms, it has not been asked well. DMG is a special category of ligand that is known as chelating ligand or chelating ligand. Now chelating ligand or chelating ligand, a ligand which forms closed ring with the central metal. Look here, a closed ring here, a closed ring here. So if any ligand has tendency, क्या मैंने बोला? What I say? Any ligand forming closed ring with our central metal is what? A chelating ligand. So DMG is also a chelating ligand. It forms stable rings, closed rings with the central metal. So it is all about DMG. Take a good screenshot of this and we will move forward. Next up we have is a tridentate ligand. Tri and tetra are not so important because they are not being asked frequently in our exams, but still you need to know. Let's talk about a tridentate and a tetradentate ligand. Tri means 3 lone pair. The example is dien. It is the brother of En, ethane 1,2 diamine. Now the structure goes like this: NHCH2 CH2, CH2NH2 and CH2NH2. Look here, donor number 1, donor number 2 and donor number 3. So we have this 3 donor atoms, that is dien, our tridentate ligand. Next is tetradentate ligand, and the example is NTA3-. It is not National Testing Agency, it is nitrile triacetate. Look here, N along with 3 CH2CO representing our acetate ion, CH2CO. So triacetato, and this N is nitrilo. So nitrilo triacetato, NTA3-, a tetradentate ligand, 1 lone pair from here, this donor and this donor, this donor and this donor. Total 4 donors, 4 lone pairs are donated to the central metal. So we have this tridentate, we have this tetradentate. Moving on to pentane hexadentate. Just give me a second to clear this. Penta is not the the best of the examiner, but hexa, that is an important one. Now look here, we have pentadentate. Penta means 5. The example is EDTA 3-. Hexadentate. The example is again EDTA but 4-. This is the most confused question about EDTA. 4- is hexadentate and 3- is pentadentate. First of all, you need to keep this in your mind. Now, as far as the full form goes, EDTA, ethylene diamine. EDTA, T means tri, acetate. Now let us start our structure. First of all, sketch a ethylene diamine, EN, CH2NH2 and CH2NH2. That is our ethylene diamine. We have triacetate, so we will add 3 acetate group, removing the hydrogens. So look here, CH2COO minus 1, CH2COO minus 2, and from here we will remove 1 hydrogen and CH2COO minus. This is our pentadentate ligand. Look closely. The first donor atom is this, the second donor atom is this, the third donor atom this one is 4, this one is 5, and -1, -1, -1, that will give us overall -3. EDTA 3-, ethyl diamine triacetate. Now the next case is EDTA 4-, that is what? Tetraacetate. It is tri, it is tetra. Same goes with this structure. We will remove this hydrogen and not here, I will do it here. CH2, CH2, again N, N, and the hydrogen has been removed and 1 acetate group has been added in place of it. Look closely, you will find it. So these are our tetraacetate. 1, 2, 3, 4. -1, -1, -1, -1. That will give us -4 here. And the nitrogens, these are the 2 donor atoms here. And there are 4 donor atoms here. Hexadentate, EDTA 4-. 4- is very important because the structure has been asked in our IIT exam. What is the structure of EDTA 4-? And EDTA 3- is yet to be asked. So it's all about hexadentate and pentadentate. Now one more thing about this EDTA, or one or few more things about this EDTA is, I will rub this up so that I can show you the classic questions asked from it. First of all, it is a chelating ligand, again very much like our DMG. It is chelating ligand, it can form closed ring. Next up we have is, it is flexidentate. Now this is a new term. It is a flexidentate ligand. So what the hell flexidentate means? Flexidentate means it can show multiple denticity. It can donate 1, 2, 3, 4. 4 lone pair of electrons and it can act as a tetradentate ligand. However, it can also donate 6 pair of electrons and can act as a hexadentate ligand. So our EDTA can show multiple denticity. It has tendency to donate 4 or 6 lone pair of electron, hence it is called a flexible ligand or flexidentate ligand. Now it is very important its uses. EDTA is used to estimate or to test calcium ion or magnesium ion in aqueous solution, or in chemical words we can say it is used to estimate the hardness of water, whether our water has excess amount of calcium or magnesium ions which can cause kidney stone, most probable. So hardness of water is judged by what? Hardness of water is judged in terms of presence of calcium and magnesium, and the estimation of calcium and magnesium is done by our EDTA. So it is all about EDTA. Now moving on to the next part, we have, hold there, we will discuss ambidentate ligand and then chelating ligand, and then our denticity is done. So what does ambidentate means? Dentate ligand. So ambidentate ligand is basically a simple ligand which can donate more than one lone pair from 2 different donor atoms. Now look here, if you have CN, you can donate from carbon and get bonded with the metal, or you have the other option, nitrogen. If carbon is used, then the species is cyanoia or cyanido. If nitrogen is used, it is isocyanido. But it will use carbon or nitrogen, not both at a time, only one at a time. So ambidentate, it has 2 donor atoms, 2 or more donor atoms, but uses one at a time. One at a time. Same goes with SCN. Whether you want to get this with sulfur or nitrogen can also be a good donor. Same goes case with NO2, nitrogen, or ONO, that is our oxygen. So it is ambidentate ligand, a ligand with multiple donor atoms, but one of the donor atom will act as the donating species at one particular time. In the next case, that will act as the donor atom in forming a different set of complex, what I can say. So this is our ambidentate ligand. Next up we have is chelating ligand. I will clean this up. Now this is an important one, chelating ligand. So I told you before that these ligands form closed ring. These form closed ring with our central metal. The ring formation, that is a stabilizing phenomena, hence our complex formed will be highly stable. So if I say I have a query for you, I have COCl6, let us consider 3 plus, and I just add up some En in it, and a new complex is formed, that is COEN3 2 plus. So can you predict whether this reaction goes? Point to be noted, it will go forward. Next option, backward. Next option, it will be in equilibrium, or none of these. Yeah, none of above. So what do you think? Forward, backward, equilibrium, none of the above. The answer is this reaction will go in the forward direction. En, ethylene diamine, it is a chelating ligand. I will show you an example. Look here, if I have this platinum surrounded by 2 ethylene diamine or 2 molecules of ethane 1,2 diamine, just give me a second to sketch this beauty. Now the donor atoms 1, 2. So here we go donation, here we go donation. 1 and 2. Overall 2 plus charge. A 5-membered ring here, a 5-membered ring here. A closed ring is formed. So this this complex is highly stabilized because formation of ring occur here. So if you have En here, this reaction tends to go forward. It will go in the forward direction because the complex form in the forward direction will be more stable. It is a bit more stable. The stability increases with the addition of En, and the stability of this complex is less in compared to this one. This overall effect is called chelating effect or chelate effect, or one more interesting name, the difference in the stability of complexes having chelating ligand in comparison to non-chelating ligand is also termed as macrocyclic effect. That is an important one. So remember this, what is macrocyclic effect or chelate effect? It is nothing but the stability of our ligand forming closed ring will be more. So the thermodynamic explanation to this effect is the increase in the entropy that your teacher has taught you in the previous classes. So finally, on the basis of denticity, we have finished the task: monodentate, bidentate, tridentate, tetra, hexa, ambi, flexi, and this chelating ligand. Let us move further. There are also many cases of chelating ligand. En, I have shown you DNG. EDTA is also chelating. Also one other example is C2O4. It is also a chelating ligand. So finally, moving on to the last section on the basis of type of donation of lone pair. This donation of lone pair we are talking about is a bit different in some cases and a bit complicated in some cases. So the first case is sigma donor. It is of three types. First of all, the type of donation is three types. First of all, we have this sigma donor. These are the ligands. Suppose this is our metal and this is our ligand. It is going to donate, and there will be a sigma type bond formation between the metal and the ligand. So this will be called a sigma donor, also called simple ligand, also called classical ligand. Sigma donor, simple ligand, classical ligand. The ligand forms a sigma bond type bond with our metal. The example is H2O, CO3 maybe, another is NH3, and so on, cyanide also. So these are our sigma donor. Next is our pi acid ligand, and also known as, I think, pi sigma donor, pi acceptor. Now these are a different category of ligand. These are very demanding in nature. Suppose this is our metal, this is our ligand. It will give its electron and form a sigma bond like bond. However, it will also ask the metal to donate or to share its electron cloud with the ligand. So its electron cloud will be shared with the ligand, and this will be shared in its anti-bonding orbitals of ligand. So this is called a pi acid ligand, sigma donor, pi acceptor. Acceptance is done in what? Pi orbitals, anti-bonding pi orbitals of the ligand, and the metal is bonded with the ligand through a sigma bond, sigma like bond. So this is our pi acid ligand. There are two particular examples of this. There are many, but I will taught you only two, that is NO and CO, CO being very important. So the last case is what? Our pi acceptor and pi donor. These are the ligands which form a pi bond type linkage, or you can say these donate pi electrons to the metal. So the ligand, metal, and pi electrons are donated. Pi electrons are donated by species having multiple bonds, like acetylene contains a lot of pi electrons, and the most favorite case is benzene, filled with pi electrons. So this will be a pi acceptor, pi donor type. So this is all about ligands. I hope you love it. I know if you are watching this till the end, share this with your friends. And what can I say? In the next clip, we will discuss coordination number, VBT, and Werner's coordination theory. Thank you for watching.